Mm. Good evening, Anish. Can you hear me?
Yes, sir.
Okay. Have you got the opportunity to watch all the videos of this week?
Sir, last two I couldn't watch.
Ah, couldn't complete. But how are you finding the course? Uh, is it helpful? Is it difficult? Is it easy? Uh,
Yes. Last 2 weeks, no problem, but I felt a little bit difficult in that uh, before classes. That weighted residual method
uh,
and all.
okay, okay. Initial weeks you were feeling the difficulty, but now you think you are understanding what is going on.
Yes.
Okay. Okay. So as we go on deep into this course, so we are like we will be experiencing more and more difficulty in understanding. Like, but you have to stick on with the course. That's the thing because finite element is that kind of subject where you will there will be a lot of gaps while you go on through these lectures. You try to uh, understand what is being taught, but when you finally solve a problem, take a example problem and finally solve it, that will give you a clear understanding of what is going on and what have you learned till now. So you will be able to connect all the dots from start to the end. So if you are like facing any difficulty uh, now, maybe like going deeper into the course, you will be able to understand more like why we are doing what we are doing, and all these things will make sense. Maybe if you are like stuck, I would suggest to listen to the lectures carefully and or probably read the notes or take a textbook and read and get some understanding. Obviously, there will be some gaps, but if you go ahead with it and try to understand and solve some problems, at the end you will be able to understand. So that's what I would suggest. So, so we are in week 6 of this course, which is on finite element method and computational structural dynamics. And this is, as you know, this course is taught by Professor Manish Shifande from IIT Roorkee Department of Earthquake Engineering. And I am Syed Shabir Ahmad, your TA for these problem solving sessions. And I'm having a PhD here in IIT Madras in the Department of Applied Mechanics and Biomedical Engineering. So, till last week, we have seen um, uh, computational computational efficiency using FEM, all these things, 1D problems we have solved, interpolation, we have learned about interpolation, and we have learned about solving a bar problem, a beam problem, which are both 1D problems. And then we have entered into 2D, three-dimensional, and then we have simplified and idealized it to two-dimensional problem. And we were going through triangular element, lateral element, and we were learning how to construct interpolation functions and how to do this integrations. So we are continuing with that the same thing in this week also. So there are like a lot of things which were discussed, but uh, instead of like just going through the concept, like this will it will be difficult. It will be easier to understand by doing and solving some problems. So uh, so let's take this. This is a element. So this is a quadrilateral element. So now I want to find out the shape functions using Lagrangian and serendipity family. So serendipity family and Lagrangian family are like different sets of shape functions that we can obtain by using these two methodologies. Like in Lagrangian, if I want, let's say, a quadratic shape function, I'll take one, two, three, four, all the vertices of the quadrilateral plus this uh, middle of the edge nodes and one internal at the center of the quadrant. So I will take total nine nodes. But we can also obtain quadratic shape functions by using serendipity method. Like in that, what we do is we just uh, eliminate this internal node. So eliminating this internal load has a lot of advantages in integration and interpolation that we will probably look when we go deeper into uh, using these elements, because this will have an understanding, and you'll be able to understand more like when we solve a bigger problem. But for now, we the problem is to just find quadratic shape functions for this quadrilateral using the uh, Lagrangian approach and the serendipity approach. So first, first I will take for this quadrilateral, and I will try to find out. Let's say this is quadrilateral. Let's see. This is my quadrilateral, and first I will use the Lagrangian family. So we'll see how we can find out using uh, quadratic shape functions using the Lagrangian approach. Okay. So in Lagrangian approach, we have to take nine nodes. So all the four vertices, so quadrilateral plus middle of the edge, I will take one node each. So four nodes in the middle of the edge and one node here, the center of the. So I'll start the numbering from here. One, two, three, four, and I'll start again from here. Five, six, seven, eight, and so I'll start. I'll draw a few lines so that I can get a good idea of the coordinates of this given quadrilateral. So this is x is equals to 0, and this is x is equals to 1.5, and this is x is equals to 3, and this line is y is equals to 0. this line is y is equals to 2 and this line is y is equals to 4. Because these are drawn based on this coordinates given for that coordinate. Okay. So now, in last week itself, we have seen we can derive shape functions uh, based on the approach which we have seen. So there was a quadrilateral like this, four-noded quadrilateral. So and we have to first like uh, anywhere we have to like find out uh, shape functions for any shape or for any element. First, we should take this uh, coordinate matrix. So coordinate matrix, we should take the terms in this coordinate matrix like this based on the Pascal triangle. So first we will draw the Pascal triangle and let's look at how we can select the nodes for this. So Pascal triangle will be like this: x square, xy, y square, and this will be x cube, x square, x square, y square, xy square, y cube. Yeah, since I want only quadrilateral, like only quadratic polynomials are quadrilateral, I'll stop it here. So I have no 9 nodes. I have 9 nodes. 1, 2, 3, 4, 5, 6. Total 9 nodes I have. So I have to select a polynomial. I have to assume the solution. Let's say u of xy. I'm assuming the solution. I have to take a polynomial with 9 independent terms. So I have to take a naught plus a1x plus a2y plus a3xy. So plus a4 x square plus a5 y square. So so till this part we have covered all the terms we have taken in this. Till this we have taken all the terms. Okay. So how many are there? 1, 2, 3, 4, 5, 6. Yeah. Plus I can take a6, 6, 7, 8. Yeah. I can take these three. A6 square y plus a7 xy square. This is yeah. Stay here. Yeah. This doesn't come first. This doesn't come. This comes here. Some mistake. This x power 4 and here I get x cube y. Here I can get x square y square x y cube and y power 4. Yeah. Thank you very much. So I have so total I have to take 9 terms. So because there are 9 nodes, so I should have 9 independent terms in my approximate solution or like interpolation function. So I want to take 9 terms. Till here, you can see there are 6 terms. Till here, I have to make arrangements for the other 3 terms. So I have to go for higher order polynomials. So I cannot take this. I cannot take like this. Like these 3 terms I cannot take because this is breaking the geometric isotropy. I cannot take like this also, because this is also breaking the geometric isotropy. So instead, I will take this x square y square term. So now you can see this is all the terms I am taking are symmetrical in Pascal triangle. So this will not break the geometric isotropy. So I will take uh, x square y square, uh, sorry, x square y, xy square, and x square y square. So three terms I will add in addition to the lower order polynomials, so that I'll get 9. So a naught to a8, I have 9 independent terms. So like this, now I have to write the coordinate matrix. So the coordinate matrix will have one x1 y1 uh, x x1 into y1 and x1 square y1 square and x1 square y1 x y1 square plus x1 square y1 square. So similarly, I have to do it for uh, x2 also, x2 y2. So like all this for 2, for 3, for 4 till 9. So I will write the coordinate matrix. Like this is a huge coordinate matrix. So at the end, I will write x1 y9, x9 y9, x9 square y9 square, x9 square y9, x9 into y9 square, x9 square y9 square. So I have written the coordinate matrix. Now we know that u of x comma y can be written as 1 uh, x y x square. Let's add a bit. X y square and x square y xy square x square y square into a naught uh, a1 till a8. So this uh, this is my approximate. So now I want to replace this a naught a1 a2 a3 in terms of the nodal displacement. So that I can do by taking the inverse of coordinate matrix. So I can take whatever this till square y square is there into C inverse into u naught u1 into u1 to u9. So now if I do this into C inverse, I'll get my some matrix I'll get. So which has a shape of uh, this is 9 cross 9 and this is 1 cross 9. I'll get a 1 cross 9 matrix. Okay. So and each term will have the shape functions from n1 n2 to 9 shape functions we will get. So first element will be the first shape function, second element will be the second shape function, and the last element will be the last shape. So like this we can do, but this is a very very huge process. Like you have to code it, and like you probably can use Python or MATLAB or Mathematica if you know any coding software. Then probably you can do it in a very easy manner. Because you just have to write some code and the computer will do the calculations and simplify it and give it for you. Okay, this is one approach by which I can get the shape functions. Another approach is also there, uh, which is simply like take this quadrilateral take this quadrilateral approach because this is Lagrangian family. Like you can just use this approach. Just simply draw it. So this was 0, comma 0. This was 0, comma 3, and this point is 0, comma 1.5. We'll say. This, 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 this. Yeah. And here central node is there. This is this 2, comma 3, and this is 4, comma 3, and this is 4, comma 1.5, and this is 2, comma 1.5. This is uh, 0, comma 4, 0, comma, sorry, 4, comma 0. I've written it wrong. So this 1.5, comma 0, this 3, comma 0, this is 3, comma 2, and this is 3, comma 4. This is 1.5, comma 4, and this is 0, comma. And this is 1.5, comma 2. This is 0, comma 2. So these are our 9 nodes and their coordinates. So now I want, I'll write 1, 2, 3, sorry, I'll use a different color. This is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9. So now if I want a shape function for N1 shape function I want. So first I will take all, uh, let's say I just have this line. Okay, I just have this line. I just have this line. Okay, let's say this is only in one dimension and there is only x. Now, how do we write the shape function? We just take what are the terms are there. We will take fifth. Okay, we will start with second node. So we have 1, 5, 2, right? So on that, what are the x coordinates? So x minus 3 into x minus 1.5. Okay. divided by, we will write 0 minus 3 and 0 minus 1 point. So this, like you might have, like we have already learned this linear shape functions. Into, now you take this line also, this line also, and now you write only the shape function, consider, like assuming that this is 1D in y. So a line is one dimensional in y, right? So I can just take y minus. So except this, I have to take two. Yeah, Lagrange interpolation. Yeah, that's what we are doing, right? Lagrangian interpolation. So instead of taking this cumbersome approach of taking the coordinate matrix, doing the inverse, this is kind of a shortcut for doing the Lagrange interpolation. So now you can take, you want shape function for this. So now you take these notes and you write the numerator. So this and this 4 and 8. So you will take y minus 0, y minus 2 into y minus 4. So y coordinate is 2 and 4 for point nodes 4 and 8. Divided by, here it is 0, right? So y coordinate is 0, 0 minus 2, 0 minus 4. So this is my first shape function. So n1 will be equal to x minus 3 into x minus 1.5, y minus 2, y minus 4 divided by, so 4 to the 8, 8 3 the 24, 24 into 1.5, you will get uh, 36. So like this, we can simply write the shape functions using Lagrange interpolation formula in 1D. So like you can just write it as, let's say, this is there. So this is nothing but, let's let's write it like L1 of x, and this is nothing but, instead of L, I'll give it a different name, M1. So similarly, I can write the shape function for n2. If you look at n2, this point you have to, now you have to consider these 2 points and write the numerator. So that is x minus 0 into x minus 1.5 divided by 3 minus 0, 3 minus 1.5. This is my L2 of x. Second Lagrange interpolation for second point. Interpolation function for second point. Now, similarly, I can write for this, like this was for x. Now we have to do it for this. So we can take uh, here. Still, you can see I'm writing for this point, so I have to consider this point and this point, these 2 points, and write the numerator. So that is y minus y minus 2 into y minus 4 divided by, again, 0 minus 2, 0 minus 4. So this is my n2. So now let's write for n5. So n3, n4, all these things you can do. Now let's write for n5. So n5, you can see this is the quadrilateral, and this is my fifth point, and this is n1 will give
Actually, sir, hello. Can you hear me?
Yeah, yeah, yeah,
Can you hear me? Yeah. So
yeah.
I was having a doubt. I think
Mm,
normally linear shape functions, n1
mm.
should have, let's say, one unit value at that point and zero at all other points. Am I right?
Yeah, yeah, yeah,
Generally.
yeah, yeah.
So here this n1 will have may have non-zero value at let's say point 0.9 because you have not included that point 0.9 in your derivation. If I am not right wrong, does that
Point
make
nine.
sense?
Okay. Yeah, 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 yeah.
So is
Just,
that okay?
just check. Uh,
Because for 2D also, shouldn't it be like that shape function should have one value at
no, you will
the
get
point which
you you will get zero. You will get zero, right? N1 will be zero at uh, point nine. I mean, the node nine.
it will be okay. I did not check. I just since you did not include that in your calculation, that's why I had a doubt.
No, we have included, right? Two also we have taken this. Let's say at point nine, the coordinates are 1.5, comma 2, right? If I substitute x is equals to 1.5 and y is equals to 2 here, this will become 0, right?
Yeah, yeah, right. Oh, sorry. Okay, correct, correct.
Yeah,
Okay, okay.
yeah, yeah, yeah.
Right. Okay, sorry.
Okay. Yeah, it's fine. This property has to be satisfied. This shape function n1 should be 1 at point 1, and other nodes, all the other nodes 2, 3, 4, 5, 6, 7, 8, 9, it should vanish. Like n1 should become 0 at all the other points. Like if you substitute x and y of other nodes, this shape function should vanish. That Kronecker delta property should be satisfied. So yeah, obviously, like you, because you raised this, this is a very important point. Like we have to keep uh, uh, we have to keep remembering this, that whenever we write shape functions, we have to do this cross check. Like if this property is getting satisfied, if it is satisfied, then it's fine. Like whatever the shape functions you are writing, otherwise uh, we have done some mistake. Okay, so now if I want n5, so I will take this and I will take this line. So, and I will write linear, one dimensional quadratic shape function uh, for x and y. Let's see how we can write. So this coordinate is, let's say first I want to write the numerator for x. Okay, so I have to consider this point and this point. No, so then I will take x minus 0 and x minus 3 divided by my point 5 has the x coordinate of 1.5, so I will substitute that in x. So numerator you have to same thing. Numerator you have to write by substituting the value of x for that point. Similarly, I have to write for this. So I will get y minus 2. Now I have to write for y, right? So I have to consider these 2 points and write the numerator. Y minus 4 divided by, now this is again same thing. This is 0, y is 0 here at point 0.5. So I'll write this. So this is how I'll get shape function for node 5. So similarly, I can write shape function for 6, I can write shape function for 3, I can write shape function for 7, 8, 4, 9. All these shape functions I can write. So this is the simplest method. So like there is like very less computational calculations we have to do. Like we don't have to do inverse and all this, but because this is like simple Lagrangian interpolation, we can do this. Otherwise, uh, we have to go through the process of coding and getting the inverse and getting this functions. Okay, so like this, you can get similarly we can get we can get N6, N7, N3, N4, N8, and N9. So these are the Lagrangian family of quadratic shape functions, which we can get for this quadrilateral. Okay. Okay. Now we have to we have to get the same thing for the serendipity family. Serendipity, it has some meaning, like, but now I don't think like you will understand it. May probably in the next week or the coming weeks you will understand what is a serendipity element. Serendipity. Serendipity is nothing but like something good happens by accident. Which all we have to take for N9. N9. Okay. So I'll write it. N9, if I want to get, let's say for N9. So this is 9, node 9. So now I have to take this for X and this for Y. Okay. So I want to write, uh, let's say one dimensional interpolation for this point using point 6 and 8. So I will take X minus, this point has a coordinate of X coordinate of 8 has a coordinate of X coordinate of 0, and 6, node 6 has a X coordinate of 3, divided by this 9 point has a X coordinate of 1.5, and so I'll substitute X as 1.5. Similarly, Y I have to get. For getting Y, I have to take these two, this and this, considering this, and I'll write the numerator. Okay. So I will take Y minus 0 because this point has a uh, Y coordinate of 0, and Y minus 4 because 7 has a Y coordinate of 4, divided by, now I'll substitute the Y value which I have for the point 9. So which is 2 minus 0 by 2 minus 4. So this is my shape function for 9, node 9. Okay. So we just have to divide. We just have to divide like this in form of one-dimensional shape, one-dimensional interpolation, and just multiply uh, X and Y. So for 9, you have to consider this one-dimensional, and this as another dimension, and you just have to get the interpolation function and multiply this. Okay. Okay. Now we have to go through this serendipity element. So serendipity element. Sorry, this this actually was found by accident, and like people didn't tend to like people didn't like people were like not someone who was doing using FEM find it out. I don't know whose name was this. Like who find like who found out this family of elements, who's uh, but this was very helpful because like this helped in the integration and then also in the interpolation, like because if you reduce the number of terms, obviously uh, like if you reduce the number of nodes, obviously you will reduce the computational effort, and and it will lead to less computational effort, and like more simpler calculations can be done. So so this was found out by accident. So accidentally something good was found. So that's why this was called serendipity element or serendipity family. So serendipity is nothing but like the meaning of serendipity is that only, like something good happens by accident, like that, or a happy accident is called serendipity, English word serendipity. So like if you happen to read this somewhere, so this is what the word means, serendipity. So like you didn't want it to happen, but it like happened by accident, which is a good thing. So that's why we call it serendipity. And like there is also a story. I don't know if this is true, but yeah, but there was a king. There was a king named Serendip, and he he won some war by accident. So by that this name came out. By this like by on his name, like this word came out, serendipity. So that's how the story goes. I don't know if this is true, but I heard it from my professor in the class. So probably you can, like, if you are interested about this trivia, like you can find out, search, do some search, and find out. Okay. So I will take, let's say, this quadrilateral which we had. Yeah. So now instead of taking instead of taking 9 elements, I'll just take 8 elements. Okay. So I'm taking notes. I am taking notes only on the edges. On the edges, you can see only on the edges. So all my notes are on the edges of the element. So no internal nodes are taken in the domain, like in the domain of the element. No internal, like we are removing this internal node. Okay. So in serendipity family of elements, you will not find this internal nodes. All nodes will be present on the edges only. That is a like important thing. Like when you see this kind of element with zero internal nodes and there are nodes only on the edges, then you can say that okay, this is a serendipity element. This is like you can distinguish like that. So you can use this thing to remember and distinguish serendipity element from a Lagrangian family or like other kind of. So 1, 2, 3, 4, and 5, 6, and 7, 8. So I'll have 8 nodes only. Okay. So obviously, because I have 8 nodes, I will need only 8 independent terms in my approximation polynomial or interpolating polynomial. So in Pascal triangle, I can just take 1x, x square, y, xy, y square, x cube, x square, y, xy square, y cube, and obviously we'll have this. Let's write this square, y square, xy cube, y power 4. So now you can see that we can like till now if I take these are six independent terms, and now I want other two. So like two more. So I will just take till now till this. So I will take x square y square and x square y and y xy square. So we have successfully removed this term. So we don't need this because we have only 8 nodes. So if we had 9 nodes, we obviously we had to take some other higher order polynomial term, which was x square y square, which we did in the Lagrangian approach. So because we have only 8 nodes in the serendipity family of elements, So we will take only this up to this. Okay. So we will take only 8 term. Let's say I will write u of x comma y. I can write it as a naught plus a1 x plus a2 y plus a3 x square plus a4 xy plus a5 y square plus a6 x square y plus a7 x y square. So I have a naught to a7. I'll have 8 independent terms. So now I can again write it like in this matrix or vector form like this. So y x square xy y square x square y and xy square into a naught to a7. A7. So this vector into this vector will give me this. Now I can write this as all this up to xy square into C inverse into u naught u1 to u8. Okay. So this C is already like obviously we know C what is C. C is the coordinate matrix. So C I have to write x1 y1 all this up to x1 y1 square like this. So I will have 8 cross 8 matrix. Okay. X x8 x square square. Okay. So you can write the coordinate matrix and take its inverse and multiply these two, you will get a 8 cross 8 matrix. Sorry, 1 cross 8 matrix. 1 cross 8 matrix. And that row matrix will have elements which we will take each term as a shape function of the serendipity family of elements. Okay. So this is how we can use this conventional approach or like sorry, not a conventional approach, but a more difficult approach or you can say like understandable approach because we are doing it step by step and we are understanding how this is going on. Uh, we are finding out the inverse and taking, but this is very difficult again because like although we have gone from 9 to like 8 nodes, so like size of the C matrix is reduced. So 8 cross 8 matrix is obviously easier to take inverse and do multiplications and operations compared to a 9 by 9 matrix. But this is also like a very huge matrix. Obviously, computers can do it very uh, in a very easy manner. So if you are writing a code, then it will be very helpful. Like you just use this approach, write the coordinate matrix, find out its inverse, and multiply with this. You will get the shape functions. Another approach is also there, like which is kind of a shortcut uh, or a shorthand approach. So you can take this element, serendipity element, can take. I'll just take this element uh, with nodes. With 1, 2, 3, 4, 5, 6, 7, and 8. Okay. And this we know this is 0, 1.5 comma 0. This is 3 comma 0. This is 3 comma 2. This is 3 comma 4. This is 1.5 comma 4. This is 0 comma 4. 0, comma 2. So these are my coordinates of the nodes. Now let's write the shape function. So let's say I want to write n1. So let's forget that there are middle nodes. Okay, so let's forget that there are uh, these nodes. I want to write for n1. So just take one-dimensional interpolation for this line. Forget that there is 5. Just write a linear interpolation. Forget that there is 5. So you consider like you have only 2 points, 1 and 2, and here only we have 1 and 4. Forget about 5 and 8. So I will write. So I want to write n1. So I have to take the other point. So x minus 3 divided by. So if I substitute the value of x at 1, which is 0, I'll get 0 minus 3. Similarly, I want to write for the other dimension or the direction, which is y. So I have only 4 now. So in order to write the numerator, I will take y minus 4 divided by 0 minus 4. Okay. This is one part. In addition to that, I have to take minus half of n5 minus half of, because we have not considered these points, right? Now we will take the effect of these points. Minus half of n8. Okay. If I write x minus 3 into y minus 4 divided by 12, then 1 by 2 n5 minus 1 by 2 n8. Okay. So similarly you can do it for point 2, node 2, node 3, and node 4. Node 2, node 3, and node 4, you can write it like that. So for node 2, you will have additional terms of minus half n by 6, minus half n by 5. For node 3, you will have additional terms of minus half n by 6, minus half n6, and minus half n7. For node 4, we'll have additional these terms of minus half n7 and minus half n8. So similarly, we can do it. For n2, 3, and 4. Now we'll see how we can write for this terms n5, n6, n7. For the middle nodes, how we write the shape function. The nodes which are lying on the middle of the edges. So n6. Now we'll go back to our traditional like Lagrangian approach, and we can see like let's say I want to find out for n5. Okay, shape function for n5. So now you can see on this line, like we'll divide it into two directions. So there are 3 points. So I want to write for n5. So I will consider these 2 points and write the numerator. In another direction, I have only 7. There is no middle node here, like in the Lagrangian interpolation. So, but still we are using the Lagrangian interpolation in one dimension to get that for serendipity element. So I want to write it for 5. I have only 7 here in my direction. So let's see how I will write. So I can take x minus 0 into x minus 3. And I have to substitute what is the value of x at 5, which is 1.5 minus 0, 1.5 minus 3. And in the y direction, there is only y minus 4 because only 7 is there in y direction. Y minus 4 divided by 0 minus 4. So now n5 is nothing but x into x minus 3 into y minus 4 divided by 1.5 into 1.5 minus 4. We'll get, I think, 9. 1.5 minus 1.5 minus 4. It's nothing but, yeah, 9 we'll get. So x into x minus 3, y minus 4 divided by. So this is the n5. Similarly, you can find out n6, n7, n8 like this. So I hope you have understood this. So for this is kind of a shortcut. Like obviously, people have done this. People have done this. Uh, this more lengthy approach by taking the multiplication of this into C inverse, and after getting the shape functions from that they have got this trick of like how to write the shape function for the serendipity approach. So this is something to remember. Like I cannot. This is like not a logical approach, but like you have to remember this. This is kind of a trick to write the shape functions. So first you like as I have said, for this corner nodes which are lying on the vertices of the quadrilateral, you will write linear interpolation functions, and then you subtract the uh, shape functions of the middle points. Okay, that is what we do for n1, n2, n3, and n4. Okay, then for n5, n6, and n7 and n8, we take all the points and write the Lagrange interpolation formula, and we will get the shape functions. Okay, so that is how we write the shape functions, like in an easy way, which using this shorthand trick, you for the serendipity family of elements. Okay, obviously, because like why do we need these serendipity elements is like obviously there are like lot of advantages, but let's say uh, earlier you were using quadrilateral elements with let's say 9 nodes. So like you were using Lagrangian family of elements. So each quadrilateral had 9 nodes. Let's say you had some like very huge plate. Okay, and in that there are like 1,000 elements like this. 1,000 elements, yeah, or let's 1,000 elements like this, or let's say let's just take a simple. It's very difficult to do. Let's just take 2 elements. Okay, so in this, so for 2 elements, uh, let's I have a tape plate, and I am dividing it into 2 elements. And for 2 elements, let's like this, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 nodes you have. 15 nodes means you will get a stiffness matrix by the size of 15 cross 15. So your stiffness matrix will be 15 cross 15, and you will have U, which is a vector which we have to find out, which will be of 15 cross 1, and load vector will also be 15 cross 1. Instead of this, if I take a serendipity element by removing this middle nodes, I'll just remove these internal nodes. I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 cross 13. So if I have like, let's say, a very big plate and like there are like thousands of elements here, very like lot of elements. I'm just explaining with two because it's easier to explain. So now you can see that you can see that can see that we have successfully reduced the size from 15 to 13. So obviously, if I have a smaller matrix, it is easier to deal with. Like I can easily invert this k compared to 15 cross 15. I can easily invert 15. Compared to 15 cross 15, I can easily invert 13 cross 13 because lesser number of calculations are required. As the size becomes big, this difference becomes more huge. Like let's say from if you have 1000 cross 1000, probably it will become to 900 or 800 cross 800 by just ignoring the middle elements. By just ignoring these middle nodes. So if I am ignoring the middle nodes, and I am getting approximate solution, which is not that bad. Like finally, if I compare like solution with this with like using 15 cross 15 and 13 cross 30, if I get some solution, and if I compare the solutions, uh, that is not like very much different. Obviously, like I just want an approximate solution. So if it has some error which is acceptable, that is fine for me, right? So that's what I am saying. Like if you have let's say 1000 cross 1000 elements, like if just by removing this middle nodes, you are reducing thousand right here. Like you are reducing thousand. You are reducing the matrix size by 1000. So obviously, this is a great advantage. Computational effort is decreased, and you have to do less number of calculations, and you are getting a good solution, which is not that bad. So that's why these serendipity elements, serendipity elements were very helpful. So we can see advantages of these, like whenever we can use them. All these things. In the future, I think future like next 2 weeks probably maybe there might be some discussion about this. So that's why this, as I said, this was accidentally found out by someone. Like they accidentally removed the middle node and did some calculation, and they found out that okay, removing the middle node didn't make a huge difference in the solution. So like if I'm like reducing my computations, and that is a good thing, less computational load, more efficiency, and I'm also getting a good solution. So that's why these serendipity elements come into picture. So like I would suggest like you take some problem, like probably do it as a course project, because you will understand it more. Write a code for this and get everything done. So you will understand it more, like why it will be helpful and what are the advantages of this. Like compare taking the middle nodes, and you remove the middle nodes, taking the serendipity elements, do the calculations, find out the difference, and if it is like helpful for you, and how it is helpful, how all those things you can appreciate when you do when you write your code. Or probably hand calculation is very difficult because like you cannot do inverses of 1000 cross 1000 matrices and all. So write a code and understand, and like use both the approaches and understand what is the advantage and disadvantage of this. So no matter how much I tell, like uh, it will not hit you unless and until you experience something, right? So that's why I would suggest writing your own codes. Probably uh, 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 like I want to ask you, do you know coding, MATLAB or Python or Mathematica? Are you doing any kind of coding? Both of you, Anish and Bennett. Little bit. What? Yeah, Anish.
Sir, just basics from school, not MATLAB and all.
Ah, like probably C language, something.
Yeah,
C,
C++ and all.
C++. Okay, okay. Uh, yeah, Bennett, you are using Python. That's good. Uh, you both are PhD scholars, right? Anish, you are a PhD scholar. Yeah. Okay. Probably like if you are doing some computational work using finite element, you have to learn to code. I would suggest. Okay. Uh, uh, like I use Python. Like there is also MATLAB, which is also good. But I'm just saying for learning in this course. Okay. Like you can use MATLAB if you have access through your institute. That is good. Like if you don't have access, they are not giving you access because this is a MATLAB is a proprietary software. Okay, if you have, then that's good. But like even though like I have MATLAB access, but I don't use it because Python, like in Python you can do symbolic calculations also in a very easy manner. Obviously, in also MATLAB also you can do it, but like MATLAB will not give you like good looking equations, rendering, and all those things is not very good. So people use Mathematica and Python for symbolic calculations, or just finite element. Like whenever I say symbolic calculations, I mean like let's say you have a matrix with x and y terms like that, and you want to multiply with other matrix which has xy terms. Obviously, you will get some algebraic matrix which again has terms filled with elements filled with xy like that. So this kind of calculations are like easier, or easier also, or you can say like more beautiful looking when we print it in Python and Mathematica, because uh, that will give expressions like in textbook. Rendering will be like in textbook. Square will be like square and all these things. So also Python is free to use, open source, and obviously MATLAB has some advantages, but I think for whatever we are doing, Python is also like has also become very efficient because there is a huge community and people are using it uh, like because they don't want to use this proprietary softwares, they charge a lot of money. So we can use this open source languages like Python is there. There is also a language called Julia. So Julia is a very good new alternative which has come. So Julia has uh, code like Python, and also it has the speed of C++. So speed which is comparable to C and C++. Python is like a higher level language, which is like compared to C, it will it is not that fast. But when you take Julia, the speed is comparable to C and C++. And also the like when you write in C and C plus, when you write code in C and C++, you have to write like very huge lines of code, uh, like lot of lines. In Python, it is very simple. Like you don't have to write like 4 or 5 lines of code can be written by like one line, and also there are like a lot of libraries which we can use. So that's what to make making it slower. But Julia is a language which has been introduced. Like people are working on it. Like I think it is there from probably past 10 years. Python is there, I think, from 1990s, early 1990s. Julia is a newer language, but it is much more efficient compared to Python for scientific computing. At least people are using it for Yeah, it was from MIT. It is from MIT. People from MIT developed it. So that is also like you can consider it using, because I used Julia when I was doing finite element course in my masters. Like my professor introduced to us Julia, and he made us to code in Julia all the finite element. Yeah, it has lot of libraries. It has libraries like Python. It has libraries, but only thing is like Python has a very huge community. Julia also has a community. Like you can go and search, uh, but Python is like widely used compared to Julia. That's what makes it a little more fancy. But like Julia is like, if you want speed, go for Julia, like I would say. So, but like if you want to learn Julia also, there are a lot of free resources. You can go to Julia programming. Like if you go to YouTube and search Julia programming language, you will get numerous number of videos, people teaching, like MIT profs teaching Julia from scratch, like how you do basic calculations to how you write a lot of finite element codes or all these things. So yeah, syntax is very similar to Python. Syntax is very similar to Python. Like there are like slight changes, but it is like similar to Python. Like you don't have to write huge lines of code like you write in C++ or Fortran or some other languages. So if you want to learn, like then now it is a good time to learn. So if you want to learn a programming language, I would suggest probably like instead of using this proprietary software like MATLAB, like a good thing would be to learn open source softwares like Python and Julia, because like let's say if you don't have access, because if you are in some good college, it is giving you access. In future, if you are like working somewhere like which doesn't have this access of MATLAB or some other proprietary software, then probably you have to go again to open source. And also one more important thing is like people, lot of development goes on in this open source softwares like MATLAB, Python and Julia. Lot of people write their own libraries. Like for FEM, like there are innumerable, like lot of libraries. People just do it for fun, like for learning. They write lot of lines of code and they make a library. Like if you know about GitHub, so GitHub is a repository, and they post it on GitHub. So people all around from the world go and contribute to those projects. So that's how open source projects are built. Like, but MATLAB and other companies are like they have a set of employees who are working around the world. So they do it as part of their job, and they try to make it like depending upon the customers' expectations, like whoever the customers are working for, like for whom they are working, they try to make tools for that. So there are like two different things, but uh, open source is like people, most of the people, if you go to Europe, like one of my lab mates went to Europe for a conference. Everyone was using like these open source softwares like Fortran, like for coding, like they were using Fortran or C++ or Python. Nobody was using like MATLAB or Mathematica. So that's what, like if you have, like if you learn open source tools, that gives you an edge. So because people will respect you more, uh, uh, and also you have advantages whenever like if you don't have access, like you don't need to buy this MATLAB or Python. And also like if you are uh, like let's say doing um, like if you want to do finite element simulations, obviously you can go to Abacus or ANSYS. Those are also proprietary softwares. Okay, you go to Abacus and ANSYS, And these two softwares have a very good graphical user interface, right? You just create a part, mesh it, like visually it's very appealing. Like you don't have to write any code. You just click on the like you just click, select the options, you do, and like like uh, very less effort is required, and you just run simulation, create jobs, and you run. But software is like something in the software inside some kind, like in the back end there are a lot of lines of code like which we are learning here. Like the algorithms are written based on the things which we are learning in the course. So people have written like the people working in Abacus or Ansys, they have written those lines of code and they have made a nice graphical user interface which converts your physical part into coordinates, then do calculate the like then get the stiffness matrix, get the solution, and give you a beautiful looking image with the contours of the displacement and the stresses. So obviously, when you use like if you are like someone you are just using Abacus, you don't know all these things. Like if you have not like if I tell a kid ninth or a tenth standard kid and make him yeah, like do a few examples and if I make him learn Abacus answers, probably he can do it. But he don't know like he doesn't know what is going on inside. So obviously if you are like doing the same thing daily, like if you are like designing the same kind of part or an element or a structure daily, obviously you have learned that you have a roadmap, like you just blindly go to Abacus machine, do all those things and done. But because you are doing research, whenever you are using Abacus or Ansys, there will be things which are not there in Abacus and Ansys, and you have to write the code and probably integrate in Abacus or Ansys sometimes, like lot of times you have to like integrate into those. Like if you are working on composites, there are something like user defined uh, like material properties. You like some kind of like obviously matter like Abacus and Ansys will have some kind lot of materials will be there, like composites, piezoelectric materials. You can define the properties, like you can give EG or the Poisson's ratio and make that element. But if you are like working on some new elements, obviously Abacus won't have it. So you need to give it. You need to write some code and incorporate it. So in research, I like what I want to say is in research, you need to learn to write code first. You need to learn to write code first. Whatever the programming language you use, MATLAB or Python or Julia, take simple problems like plates, beams, bars, and like whatever we are learning in this course, try to code them. So try to code them, then you will get a good understanding of how finite element is working. Okay, obviously you cannot code, like it is difficult to code for a very big machine, huge machine, which has some irregular structure like a engine or something. Obviously you will need help of these softwares like Abacus or Nastran or ANSYS. But if you don't know what is going on, it will be very difficult. Okay, so I would suggest that. Yeah, Bennett.
Sorry, by mistake.
Yeah, it's okay. So I'm just saying, please code whatever you are learning in this course, like from bar to beam to this two-dimensional things which we are. I think in class in the last week there was a bracket problem which was discussed. So that also, like each and everything you can code and like write the code and you will understand. That's what I would suggest, because you don't know until how it's like you don't know until you do how it's done. Okay, so it's like it is like FEM is a very dry subject. Like if you don't practice doing it, like solving and writing code, you won't understand it completely. Like even though I'm working with FEM like 3 years probably, but I still have some gaps. Like I don't understand a few things. So that's why I would like suggest you please, because while I was learning, I did coding, but because I was uh, because I was in IIT, so I got to learn coding because professor like will expect you to write the assignments and do assignments. We have to submit codes, so that is part of the course. Like if you it is not mandatory in this course. Like you don't have to submit assignments with codes, but if you want to learn the subject fully, please code. That's what I would say. So code and learn. There is no better advice I can give you for going through this course, because this is a very huge course also. This covers a lot of things. Like still we are in finite element. Probably in after 2 weeks we'll go into structural dynamics, and that is that makes your life very hard compared to just a static finite element which we are doing here. There you have to go and solve it for time, each time instant. Like for t is equals to 0, t is equals to 1, t is equals to 3. Numerous times we have to set. Obviously, you cannot do it by hand. Like it's very difficult to solve complex time dynamics problems with hand. So I would say, yeah. You are right. So ChatGPT is the evil which you have to avoid. So at least while learning, like if you have learned coding, like when you are doing the course, I would suggest don't use chat gpt and all. Obviously, like you just code, like learn the language, programming language, how to write functions, how to write conditionals, like if else condition, how to define symbols, how to do basic calculations, how to solve differential equations in Python, and there are a lot of things we should learn. Like there are like lot of courses also. If you want, I would give those sources also, like from where you can learn Python. So there are like huge number of YouTube tutorials from which you can learn. See about uh, but if you are like just saying like giving the problem, take the screenshot and give to ChatGPT, it will give you some code. Obviously, it gives very good code, but it gives a lot of errors also. Like while using ChatGPT, it's not as easy as we think, because like this numerical calculations and like this solving scientific problems, we have to be very particular about giving the details to ChatGPT. Like like let's say I will tell my own experience. I was using ChatGPT when it was released. I think 2.5 to 3 years ago when it was released. I was so excited. I was like, okay, this is like this will save me a lot of time. Like though I knew coding, so I started using from ChatGPT. I completely advertised it to my lab mates. Like I used to say like you have to use this. This will save you a lot of time. You don't need to write huge lines of code. You can edit your text, documents, all these things. So, but as soon as like I have used till like 2.5 to 3 years now, I have realized that okay, ChatGPT is helping me, but it is also draining my knowledge. So like I am not doing things like it, it will give you a lot of errors, and you in order to find out that error, you have to again go through each line of code, which is the same thing as you write the code again from start to end on your own. So that finding out the error again becomes a task. So like you think that you are saving time, but you are also like wasting time. So that is a big disadvantage of using ChatGPT. And also there was a study by MIT only recently that they compared two sets of people. Uh, One they made use ChatGPT, the other they didn't make them use ChatGPT for I think 2 to 3 weeks. After that, they told both the groups to do creative tasks. Okay, writing a poem or like I don't know what I forgot, but do some creative tasks. And they measured the brain signals. I think I forgot what is the name, but they measured the brain activity using some kind of a device on the brain, and they observed that who people who didn't use ChatGPT has more brain activation compared to people who use ChatGPT. So people who are using ChatGPT are not able to use their brain completely. Not completely, like obviously no one will be able to use it completely, but compared to the people who didn't use, people who are using ChatGPT or any other AI tool had less brain activation. So this is like this study tells us that somehow this uh, AI tools are like killing our creativity. So, uh, but obviously, if you are some kind of a school or a college undergrad student, maybe it is okay, fine. But if you are a research scholar who is like whose work is to read and whose work is to go deeply and deep dive into the subject and get some gap out of the subject and try to find out the solutions for the problems which are there in the subject, this is not a good thing because we need to think, like we don't have any other option. Research scholars have to think, and that is our that is our basic work, right? Like we have to go deep dive and like use our brain, find out the gaps. Obviously, you can't say like I won't use these AI tools because you have to use them, but you have to use them very wisely. Let's say I want to write a function. I want to write a basic function. Like I can ask ChatGPT, give me the syntax of this function in Python. Then I will take that snippet and copy it in my code and I can use it. But if you go and tell ChatGPT to solve the whole problem, give some problem like the problem which was solved in the class last week, you give it and you dump and ChatGPT will give you some like 1,000 lines of code. Then that will become like a huge problem because you are not using your brain. Probably when you have some difficulty in like writing something, like there are like lot of lines of code which you won't remember and like it is difficult to write. uh, in those times you can use ChatGPT. And also like when like uh, when like you are like getting some errors, like if you are writing a Python code on your own and if you are getting some error in the code, you want to debug that error. Okay, like obviously if you know it, like you can go and go to that line in which the error is there and you can debug it. Okay, sometimes you don't know it because programming is a vast ocean, like you don't know each and every intricacy of that. So what you can do is you can just copy the error message which you are getting in the terminal, and you just copy paste and ask ChatGPT to explain what is this error, why it is happening. Then it will give you an explanation, very good explanation, like this is the thing which you are like doing it wrong, you have to correct this, and you can get the answer, and like that will save you a lot of time. Earlier when I used to do coding during my MTech, when there was no ChatGPT or this AI tools, whenever I used to get an error, I used to go through each and every documentation, and there are like lot of communities like Stack Exchange on which people post this coding related queries. Like someone who knows will answer that. You have to search each and every query like Quora, or you might have used Quora or Reddit. So like that, there are a lot of communities for coding. You go and search. Like sometimes it will take 4 or 5 days, and sometimes you have to ask people in the community, and they will answer if they know. So this was the procedure. But now ChatGPT will give you in like seconds. So you just copy the error code, copy the error which you are getting, and ask ChatGPT, it will give you. So that is how like smartly you can use ChatGPT, and also you can preserve your thinking capacity. So at least while learning, okay, at least while learning, you should not use these things. After you have learned and you have understood all these things, then you can use the AI tools. That is that is a different thing. But if you are taking a subject and using ChatGPT directly to solve those problems, you won't learn anything. I I read a book. There is a book called Make It Stick. So that is a book on how to like you can probably you can also read it if you have interest. So the book's name is Make It Stick. So in that book, uh, that book is a collection of research, all the research which has been done on how to learn. So in that there are a lot of techniques and things uh, which were like people have like extensively worked and given lot of techniques on how to learn. So the essence of that book in like in one sentence I would say is that it learning will be more fulfilled if you make it more difficult. Okay, so it means like I am just saying it in one sentence. Like if you make your learning more and more difficult, you will be able to like if you let's say if you are like solving some problem, if you solve some problem like next go and take the other like more other difficult problem, like difficult than what you have solved, do it like that. So if you solve more and more difficult problems, and if you like yeah, yeah, if you do more and more difficult uh, uh, difficult tasks, your brain will like the neurons in the brain get connected, and you will be able to learn more. So that's what I learned through that book. So like if you are making something difficult, yeah, yeah, that's what like finite element is like that. Like uh, this will make you search. This course will make you search a lot because very little knowledge. Like obviously there are books for basic finite element, but what is being taught in this course particularly, uh, like professor has like deep dive into a lot of things. Like even I didn't know while I was like taking, because this course has like lot of material. When I took finite element, like only till what we are learning right now, till this was my core syllabus. In the whole semester, till this only, till 2D, it was covered. Bar beam and this 2D. Like there was no time to go into 3D also. So yeah, yeah. So but in NPTL, like because these are recorded lectures, like you do like there is like very less interaction with the class, and like you can use PPTs, so you can cover a lot of syllabus. But in class teaching, you won't be able to cover this much. So obviously, you can if you use PPT also, but when you interact with students, they will ask you doubts. So that then it will be difficult to cover. But even though like even though till this it was covered, but the courses which I took related to finite element were not as detailed as this course. Like I didn't know what like properly interpolation, computational, like this natural coordinate system. Like lot of things are there which have been beautifully taught by professor in this course. So I don't think you can get very detailed like. As detailed a course as detailed as this, probably uh, because of too much information it might seem like it is difficult, but it is also very helpful. Like if you are like giving good time to trying to understand what are the things which are being taught in the course, it will be a very good asset to you. Like you will learn a lot. So There is no doubt in that. Like you will at the end of the course, you will like probably if you even if you have learned 60 to 50%, then you will have a good edge over like the other people. I would say because this course is very good. Yeah, yeah, yeah. I also thought that like initially there were a lot of undergraduate people were also in this course. I don't know if they have left that course. They took it as part of their MOOCs. I thought, how oh my god, how will these people cope up with this course? Because in learning just finite element is difficult. In undergrad, like in MTech also it is difficult. Yeah, yeah. Success rate is terrible because like this is a very big course and also that makes it difficult because like less time is taken to cover. Like obviously things are covered very clearly, but time taken to cover those things is very less. So that's uh, one of my lab mate was also like going through this course. I suggested him like that this is a good course because he was preparing for something. So he wanted to give an interview. I said, okay, you can probably refer to this course. Uh, Topics covered in this course are good. He said after 2 3 days, I think he watched 6 to 7 weeks uh, of lectures, and he told me, "Oh my God, how are you dealing with this course? People will be dropping this course because this is not a very beginner friendly course." So I said, "Yeah, like people, I don't like a lot of people have dropped." Only people who are doing PhD can probably understand this course to an extent because you have gone through uh, theory of elasticity or solid like advanced solid mechanics. Uh, then only you can understand it. And also finite element, if you know before, and if you like a little bit of finite element, if you know before, and also vibration theory of vibrations, if you know a little bit before, then you will be able to completely understand this course with little difficulty, I would say. But if you are like fresh going to into this course, it will be difficult for you because you don't know all these things and like things are moving very fast. So things are moving very fast and like you don't have time to read and like understand those things. uh, that will be difficult in assignments where which they have given displacement of nodes and asked for stresses of nodes. Can we solve? Okay. This assignment, right? The sixth assignment. Okay. Yeah. I will see. uh, Consider a plane stress element shown in figure with node numbers, coordinates, and layers. Element is a part of a bigger mesh. Find out the stiffness matrix of the element. If under certain loading conditions, the element deforms with nodal displacement. Okay. Find out the Gaussian state of strain at those points to compute. Also find out the state of stress at those. Using the shape functions, extrapolate on the nodes using following values for calculation. And such as the okay. I don't think I don't know how they gave this question in this. Yeah, because this is very difficult to do without using natural coordinates, which are discussed in the next. So we have an element. We have an element like this. This is some element. Like we have some bigger structure in that. This is one element, and they are using four noded quadrilateral element. And okay, fine. They have given the coordinates also. Don't need to. This will be simpler if we are using -1 to +1. This is 1, 2, 3, 4. These are my XY displacements directions because this is 2D. So I will have 8 displacements. So first I can get the shape functions. So the shape functions for this quadrilateral theta coordinate. Yeah. This is natural coordinates. We call it natural coordinates because they have also given in this assignment the picture which it is given. In that also they have given node one as node one coordinates as -1 plus -1, and node three coordinates as 1 and 1, 1. So that only I have written. So I have not like modified and converted into zeta coordinates or natural coordinates. They have given this in natural coordinates. So probably if you watch next week's, like if you don't know what are natural coordinates, uh, then you should. I think we have used the bar and beam. I don't know if we have used, but uh, probably next week lectures, if you watch, you'll understand this completely. But this is simple thing. Like I'm just writing like these are the interpolation functions. So whatever I have like consider this as x as zeta and y as neta. Just do that. So instead of x and y, I'm using eta and neta or zeta or neta, whatever you want to say, these Greek letters. Instead of x and y, I'm using that. So Lagrange interpolation formulas, like you can for this four noded quadrilateral, like we can write like this. Very simple to write. Like whatever we have, like whatever the approach which we have used previously, like you can use that and you can write this. Four has 1 - zeta and 1 plus. So these are my shape functions. Now I have to get the derivatives of these shape functions with this with respect to these coordinates. So I have to find out what is d by zeta. So now n I can take like this as a vector. Okay, n1, n2. I will store this in this vector because I want to do matrix calculations. So now you do it. You like each n1, n2, n3. You will divide it by zeta, eta, and also similarly you divide it with respect to neta. You will get some vector like this. So, by doing this partial differential. Then we also need this Jacobian with respect to the physical coordinates. So obviously this they have given uh, not given any dimensions. Okay, but if you have, let's say, some physical coordinates, you can just take Jacobian. So Jacobian is like which we can use when we are converting from physical coordinate to natural coordinates. So you can write it like this: xi. This is sigma I. So sigma I theta into yi. This yi theta. Sorry, this is theta. So xi sigma. This will go on from I to n. So okay, theta by yi. This is my Jacobian. And this like this derivative in terms of the natural this our physical coordinates x and y. If I want to convert this, I can write like this. I want. I don't think we need here because already given. So if you do J inverse and into my J inverse and multiply with this, you will get dou n by dou x, dou a by dou y in terms of the physical coordinates. So there are like we need like they have given the displacement. We need to find out strain and we need to also find out the stresses. So strain displacement, yeah. X and xi and yi are physical coordinates. Physical coordinates. So strain displacement relations. So like they have already given the displacement, and from that we need to find out stress and strain. So we know the strain displacement relations. Strain displacement relations. Solid mechanics or advanced solid mechanics. So for a two-dimensional system for plane stress, because this is given plane stress problem. So these are the strains which will be there. Okay, I can write the strain vector like this. You can write strain like this. U into epsilon is equals to b into u. Okay, so b is nothing but the derivative operator. So your like u is nothing but this, right? U is nothing but n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, something like that. Okay, you can probably like take the derivatives. B you can write it like this. B is nothing the derivative operator dou n by dou x 0 dou n2 by dou x 0 dou n3 by dou x. This is already done in the class. You can check for the bracket problem. And 0. Similarly, we can write it for y 2 by dou y 0 dou n3 by dou y and 0 and dou n4 by dou y. This is for epsilon xx, epsilon yy, and now I have to write it for gamma x. This dou n1 by dou x, dou n2 by dou y, dou n2 by dou x, dou n2 by dou y, dou n3 by dou x, dou n4 by dou y, dou n4 by dou x. So this is a simple strain displacement relation. So this into u1, u2, u3, you will get the strings. And also we also know the constitutive matrix, which is the constitutive matrix for plane stress. Constitutive matrix B for plane stress. This we have derived in the last class for plane stress and plane strain. In the last session, we derived this. This is my constitutive matrix. So if I know the displacements, I can get the strains. And if I know the strains, from that I can get the stresses. So these two relations I need: strain displacement relation and stress and strain relation, which is the constitutive matrix. Okay. So elements first they are asking what to find out the element stiffness matrix. So elements uh, from like if you take the weak form and from that we'll get this element stiffness matrix. Okay. We have already got the weak form for plane stress and plane strain. From that we get that this is a standard form. Like you can just remember this, like we transpose the b det j, because we are converting it into because we are converting this into natural coordinates. This det j comes additionally. If we had xy, it won't come because we are converting it from -1 to +1. This is coming. Okay. So now I want to evaluate this integral at Gauss points. So Gauss quadrature method for integration, we have learned. Uh, we have learned, I think, in the second week. Gauss quadrature we have learned. So I want to do integration over this square. So instead of that, what I am doing is I will take 4 Gauss points. I will evaluate the function at these Gauss points. Okay, whatever. This is my function. Okay. Uh, this is my function till here. I will evaluate this. Let's say this function is f of eta comma eta, and I will evaluate this function at these 4 Gauss points, and then I will give weight some weight to these Gauss points. I will multiply with that weights and sum all the contributions of all the Gauss points. That will give me the numerical approximate integration of this. So that's how we use like instead of doing the integration directly, we use some kind of numerical technique. So 2 by 2 Gauss quadrature. So Gauss points we use will be plus or minus 1 by 3, 1 by root 3. So this is minus 1 by root 3, comma minus 1 by root 3. This is plus 1 by root 3, comma minus 1 by root 3. And this is 1 by root 3, comma 1 by root 3. And this is minus 1 by root 3, comma 1 by root 3. These are my 4 Gauss points. Okay. Like this I will use. And I will evaluate this function. Let's say I will call this function as f of eta comma eta. Okay. I will evaluate this at each of these points. And then I'll get some and I'll sum all the individual contributions. Okay. Here the weight for each of this for 2 by 2 Gauss quadrature, the weight is 1. So instead of using W, I'll just use 1. Like I'll just sum the evaluation of function at each point. Okay. So I changes from 1, 2, 3, 4. So 1, 2, 3, 4. So that's why I'm using summation from 1 to 4. So this Substitute eta I and eta I minus 1 by root 3, minus 1 by root 3 like that. Get 4 terms and sum it. That's what this summation means. And that j of eta I into eta I. Okay. Into T, this is thickness, whatever which we have. So now you will get the element stiffness which you are looking for. Element stiffness matrix. And then from that we have we have also to extrapolate stress. So you have E and U. They asked in the question for KE, I think. So KE some matrix you will get. From that you have to give some element, I think. What is that element? Strain displacement matrix. Okay, from the strain displacement matrix, you have to give element 3, 4. Strain displacement matrix. In this, you have to give the third row, fourth element. That is what you have to give. In the stiffness matrix, in this you have to give K4, 5. That you have to give. 4, 5. Okay. It's 4, 5 only. Yeah. Over. Okay. K4, 5 you have to give. And then after getting this epsilon xx, epsilon yy, and gamma xy, you have to evaluate. So you know epsilon is equals to b into u. So you have u, you have b. In b you have functions with respect to eta comma eta. Substitute eta comma eta for first Gauss point. So in B you substitute what is the first Gauss point? Gauss point near node 1. So Gauss point near node 1 is this Gauss point. Where is that? Yeah. This is my node 1, this is my node 2, this is my node 3. So Gauss point near node 1 is this Gauss point. So substitute, instead of eta and eta, you substitute minus 1 by root 3, minus 1 by root 3. And you will get epsilon xx, gamma x, epsilon yy and gamma xy at that Gauss point. In B, you substitute that, you will get it. Multiply with u, u is already given in the problem. Then you will get stresses at the Gauss point near node 1. Similarly, you just you have E, you have D, and you have epsilon. You have epsilon and you have D. So you multiply with this, you will get stresses at the Gauss point. Okay, stresses at the Gauss point near node 1. So after finding out epsilon, you just multiply D and epsilon. You will get. And then we have to extrapolate gamma xx, sigma xx, and gamma xy at node 1. So we know stresses at the like after finding out that we know stresses at the Gauss points. So like we can find out all this. We can find out stresses stresses exploration to nodes. All nodes we have to find out. So before finding K matrix, we need to find the stresses. No. First, we have to find the K matrix. K matrix can be found out without finding out the stresses. There is no need to find out the stresses, right? See, K matrix is a separate question they have asked. So you don't need any relationship with there is no relation with K and sigma here. No, can we find out stresses without matrix? Yeah. We can find out stresses without finding out the K matrix because they have given U here. U is given already here. Like in the question, they have given 8 displacements. That is the U vector. Yeah. And you know B is nothing but this matrix. You do this differentiation, you will get some B matrix, and in that you substitute uh, minus 1 by root 3 and minus 1 by root 3 for eta and neta, you will get B. And B into U, you will get the strains at the Gauss point 1. And similarly, if you multiply it, this D with E, you will get again D with epsilon, you will get the stresses at the Gauss point. So you don't need K here. K is a separate question. Uh, will be possible to such questions during a material like that. It will take much time. Uh, I don't know. Like you can solve it. This is not. Uh, they will give you appropriate time for that. See, uh, yeah, I think they will give appropriately, and also I think uh, I don't know how like you have grades. I think they will give absolute grading only they will give. If it was relative grading, because if you come here in IITs or NITs, like maybe some NITs, they have relative grading. They don't see like how much you have got in the exam and give the grade. Relatively, they give. Like if you got 70% and you are the topper in the class, you will get excellent grade like that. So I don't know how this in your colleges how it will work. Uh, but for this kind of PG level courses, relative grading is good because nobody will be able to solve all the questions. But I think in this NPTEL exam, they'll give easier questions only because you don't have time to solve. Extrapolation. So like after multiplying with it, multiplying with epsilon, I think what we have asked is extrapolated. Oh, okay. Only node one they have asked the extrapolated. So you get sigma at the Gauss points. Okay, after multiplying d and epsilon. So this is epsilon at the Gauss points and sigma at the Gauss points. So we can approximate the stress field by using the same shape functions. Like displacements are also we are using interpolation functions and approximating over the whole field, right? So similarly, we can use this strategy for stresses also. So stress at any point, eta comma neta, any point can be taken as this summation from sigma n into nn into theta. So this n means I am let's say if I node, let's say if I know the stresses at nodal values, that is sigma n. Okay, I know the stresses at nodal values, sigma 1, sigma 2, sigma 3, and some sigma 4 like that. Nodal values if I know. And I want to find out stress anywhere in the middle, I can use this interpolation formula and I can find out. So if you have, let's say, I want to find out stress at the four Gauss points. Four Gauss points will be eta 1, eta 2, eta 1, eta 1, eta 2, eta 2. Yeah. You have found out stress at Gauss points. Why you can put node coordinates? Why can we put node coordinates to get stresses at those nodes? But the stresses which we get here, yeah, this sigma GT which I get here are numerical values. Like I cannot substitute any eta and eta here. These are not numerical. These are not expressions. This sigma GT which I get here is a like these are all numerical values. From this numerical values, I want to extrapolate and go to the outer nodes. Okay, so I cannot substitute eta and eta directly here. Sigma eta 3, eta 3. Let's say these are all the stresses at the Gauss points. Okay, we have just found out this. We have just found out this. There are like all the other Gauss points, right? Uh, at those Gauss points, these are all the stresses at those Gauss points, which is equals to n into n matrix, or like n1, n2, n3, and n4 into sigma 1, sigma 2, sigma 3, and sigma 4. Sigma 1, sigma 2, sigma 3 are my nodal stresses. Okay. So I have this already here. I have this already. I have found out by my calculations. Now I want to find out this. Nodal stresses are not derived. So now I want to find out this. So I can take sigma nodes is equals to n mat inverse into sigma GP. Okay. Here n mat is a 4 cross 4 matrix because you are evaluating n1, n2, n3, n4 at each Gauss point. Okay. Eta 1, eta 1, eta 1, eta 1, like that. Here n1, eta 2, eta 2, like this. So at 4 Gauss points, you will evaluate and you will get this matrix. And if you invert this matrix and if you know this sigma GP, you will get sigma nodes. So that's how you can extrapolate from Gauss points to the nodes. Okay, you will get this. This is like a coding problem. Like you cannot do it with hand. So you have to code it. I would suggest you to code it because you will get because you have here 8 degrees of freedom, right? At each node there are 2 degrees of freedom and there are 4 nodes. So you'll get 8 degrees of freedom. So for each degree of freedom, you'll get 2. For each node, you'll get 2 degrees of freedom. So you'll get K matrix as 8 by 8 matrix. So you cannot do it with by hand. Okay, so probably, not probably, definitely you have to use, you have to do coding. So K matrix is a 8 by 8 matrix. You do coding and you find out the K matrix. And from that you need to find out what is K45. And B is like something like B is like something you can do with hand calculation. But K, for K, finding out K, you have to do coding only. I don't think there is another way. Like by hand calculations also you can do, but it's like it will take a lot of time. And then you can find out epsilon, sigma for the Gauss points, and from the stresses from the Gauss points, then you can go and find out all the nodal stresses if you want. What are the stresses at node 1, node 2, node 3? So all those things you can find out if you if you don't know now how to code, like probably ChatGPT will give you an answer, but please don't do that. Just go and code. It's not very difficult. Uh, it's very easy process only. Did you understand how? Like I've just given you outline how to go about this. You can code it and do. Is it fine? Then anybody is there? Yeah. Okay. Any other doubts you have, or we'll close the session for today? Okay. Think no other doubts. Okay. We'll close the session for today. Thanks for joining. Probably I'll write in the next week. I'll write a Python code, maybe uh, from the book, from the example of this week, or like maybe some other example I'll take, and I'll write a beautiful Python code, and I'll explain how you can go about coding. It will be very simple. I'll share also the code. Yeah, yeah. Okay, okay. I'll solve and show you. Okay, it's not a big thing. So we'll see how we can use coding to our advantage. From next, or like every week, we'll go. I'll code and show you how things can be done. Okay, and I'll also share the codes with you. Then you will be able to learn better. Okay. Okay, guys. Thanks for joining. Have a good night. We'll meet in the next one.
Thank you.
Thank you.